Metal fatigue is a serious issue that often goes unnoticed until it's too late. It occurs when metal parts weaken over time due to the repetitive application of stress and strain. This weakening happens because of the repeated stress and loading that metal components endure during their operational life. Imagine bending a paperclip back and forth. Eventually, it will break. Metal fatigue is similar, but it occurs on a microscopic level. Over time, this can lead to the formation of tiny cracks, which can grow and lead to complete failure of the metal part. This can have disastrous consequences, especially in critical industries like aerospace and construction. Think about airplanes. They experience constant stress during flights, from takeoff to landing, and even during turbulence. This makes them particularly susceptible to metal fatigue, necessitating rigorous inspection and maintenance routines. A small crack can propagate and lead to catastrophic failure, endangering lives and causing significant financial loss. Similarly, bridges and buildings are also at risk. They bear heavy loads and vibrations, which can cause fatigue over time. These structures are subjected to constant stress from traffic and environmental factors, making them vulnerable to metal fatigue. Predicting and preventing metal fatigue is crucial for safety and reliability. Advanced technologies like AI and predictive maintenance are now being used to monitor and mitigate these risks. For years, engineers have relied on traditional methods to predict metal fatigue. These methods have been the cornerstone of ensuring the safety and durability of various structures, from bridges to airplanes. These methods often involve physical testing, which can be both rigorous and meticulous. Engineers would apply stress cycles to material samples until they fail, meticulously recording each phase of the process. This helps determine the material's fatigue life, providing crucial data on how long a material can last under repeated stress. However, this process is time-consuming and expensive, often requiring specialized equipment and extensive labor. Another limitation is that traditional methods provide limited insights, often leaving gaps in the data that can be critical. They only tell us how long a material can withstand a specific load, without offering a deeper understanding of the underlying mechanisms. They don't give us a complete picture of how fatigue develops in complex structures, which is essential for modern engineering challenges. This makes it challenging to predict fatigue in real-world scenarios accurately, where variables are numerous and conditions are unpredictable. That's where AI comes in, offering a revolutionary approach to understanding and predicting metal fatigue with greater accuracy and efficiency.